Okay, so 10.3, we're really going to start hypothesis testing. Like this whole week, we've kind of been doing like bits and pieces of it. Today, you're going to see like, we've kind of looked at the conditions-ish. Well, I haven't written them out yet. Today, we're going to look at the testing section more and the conclusion. Tomorrow, we'll really like put it all together and I'll show you a formal write-up for a hypothesis test. So, tomorrow's a big day. But today, we're just doing like a little part of it. So, again, I usually do this on Valentine's Day. According to a recent article, most people are kissing the right way. That is, according to the study, the majority of couples tilt their head to the right when they're kissing. So, first thing we want to do is define P. This would be like condition 4 when we get to our testing. State the null hypotheses and the alternate hypotheses for this question. So, like P was what we would be looking at. We're going to look at the true proportion of couples who kiss with their heads tilted to the right. So it's going to be important once we start doing our hypothesis testing that you define your p-value, your parameter. Okay. So our two hypotheses, our null hypothesis is going to be p equals 0.5. Right? You just assume that. I guess it doesn't matter which way you tilt your head. So 0.5. The alternate, we're trying to decide if the majority of the couples tilt their head to the right. So we're going to say P is greater than 0.5. Because we're looking for a majority. So, in order to figure this out, in the study, a researcher observed 124 couples kissing in various public places and found that, it's weird, 83 out of 124, or 66.9% of the couples, tilted their head to the right. Is this convincing evidence that P is greater than 0.5? That's kind of like the question that we're going to answer, really. So what we're trying to figure out is what's the probability we get a sample proportion as high as 66.9 by random chance, assuming that the null hypothesis is true. Remember, when you have your two hypotheses, you're assuming the null hypothesis is true. So if it's really 0.5, what's the probability you get 66.9? Same thing I just said. So we're going to do a quick simulation to figure this out. So we're going to assume our population proportion is 0.5. So everybody take your calculator. I think we have to do the birthday thing. Otherwise we'll all get the same number. So put in your birthday. Either the month, day, year, it doesn't matter. Hit the STO button. Go to math. PRB. Hit rand and then press enter. So now hopefully we all won't get the same number. So we're going to all go out, simulation, and watch 124 couples kissing and get a certain proportion. So go to math again. Go over to probability. And go down to number 7, rand bin. Does anybody's come up with like a checklist? Okay. You're going to put in 124 because that's our n value. Those of you who looks like mine, put in a comma. P value should be 0.5. Does yours ask for a frequency? Repetitions, just do 1. Everybody else, you can just close your parentheses. Because we just want one number, because we're all going to go out and take one sample. Now press enter. And it might take a second. So everybody should get a certain number. So figure out your p hat. So do whatever you got in your calculator divided by 124. That's your p hat. and round to the nearest hundredth. So mine was 0.46. So what we're going to do, we're going to create a class dot plot. And I was going to do it on the board, but since there's not that many of you, we'll just do it on the paper. So what we're simulating here is all of us going out, like I said, and doing a sample of 124 couples and getting a certain p hat. Because we're going to try and find the probability that they got such a high percentage. Okay, so mine was 0.46. Josh, I'm going to start with you and we'll snake around.
0.52.
0.39.
49?
0.48.
Oof.
0.52.
Oh.
0.52.
Doesn't matter. Beverly.
0.49. 0.48.
Derek.
0.49. 0.41.
Hannah.
0.42.
Okay. So, let's look at ours. The majority is between I think the lowest was 0.39 and the highest is 0.59. This person in the article got 66.9. They got this number. So there's two explanations for this, based on if you just look at our simulation. There's no direction, there really is no direction preference. We just got 0.669 by random chance, which is highly unlikely if you're assuming it's 0.5, right? Because look at all of ours compared to the one that they got. Or that the null hypothesis, or the alternate hypothesis really is true and couples prefer to kiss to the right. So, since it's extremely unlikely to get a sample proportion of 0.669 by chance, if the true proportion is 0.5, we end up rejecting our null hypothesis and concluding that the majority of couples actually do tilt their head to the right when they kiss. Because if the null hypothesis is true, we should get something way smaller. So we will reject this and go with this. Okay, it seems weird because you're assuming that the person who's doing this study is doing everything right. So this is not by chance. So we're then rejecting this and going with this. Now, flip it over. Because you can't always do a simulation. There's got to be some like calculations of math behind that conclusion. So when we do a write-up for hypothesis testing, you have to do what's called a test statistic. It's the function of a sample data on which a conclusion to either reject or fail to reject is based. So what we're going to do is we're going to take our test statistic, it's basically a z-score, and we're going to find a p-value. The p-value is the measure of inconsistency between the hypothesized value and the observed sample. So this is important to know. The p-value is a probability, assuming the null hypothesis is true, of obtaining a test statistic at least as inconsistent with the null hypothesis as what it actually results. So like it's the probability you get what you got if the null hypothesis is true. So the probability I would get 66.9 if the true proportion was 0.5. So that's what our p-value is. It's a probability, hence why it's p. So whether or not we reject or fail to reject the null hypothesis depends on the p-value. And here's what you remember, and it's cute and funny and you'll remember it. If the p is low, reject the hoe. You'll remember that. If the p-value is less than or equal to our alpha value, we reject the null hypothesis. Okay, we talked about alpha yesterday. If the p-value is greater than alpha, we fail to reject. Okay, and remember, alpha depends on which type error you think is worse, right? If type 1 error was bad, yesterday we talked about you pick a low alpha. If type 2 error is bad, then you pick a higher alpha. If it doesn't matter, you stick with 0.05. And sometimes they'll give you an alpha value. Or if they don't, sometimes your p-value is greater than all three, less than all three. So it doesn't matter which one you pick. So like if you think about, remember our normal distribution that we looked at first semester? Basically our alpha value is like the area under the curve. When I took this class, my teacher used to call it the rejection region. So like we would have an alpha of like 0.05. That would be, if the area under the curve is 0.05, less than 0.05, we're going to reject the null hypothesis. We're going to find a p-value, it's a probability. So if our p-value is 0.03, we're in this region. We're less than 0.5%. So we reject. Okay, so let's do this problem with the math, and you'll see kind of what I mean. So, because obviously we can't keep doing simulations, because it just takes too long. So we're going to use our knowledge from Chapter 8, which is why I said Chapter 8 was super important. So, in the kissing example, we start by assuming the null hypothesis is true, that p is 0.5. Then we find the probability of obtaining a sample where 83 out of 124 kiss the right way. This was 0.669. Given that the population proportion p is equal to 0.5. So when we do our test statistic, it's just another name for a z-score. We're basically finding a z-score. So remember our z-score formula. Here it's going to be p hat minus p divided by the standard deviation of p hat. So that's why you have to remember your Chapter 8 stuff. So we already have p hat in this example. It's 0.669. Your p is whatever your hypothesized value is in your hoe and your hop. So here's 0.5. The standard deviation we got to remember from Chapter 8, which for a proportion we did p times 1 minus p divided by n square rooted. If you remember that. If not. So it's going to be 0.5 times 0.5 divided by 124. You guys actually did a lot of this in Chapter 9 too. It's like the second part of your confidence interval. Whatever you did after Z star or T star. Okay, so let's find this z-score. So 0.669 minus 0.5 divided by 0.5 times 0.5. 0.0449 would be the standard deviation. 0.669 minus 0.5. So we get a z-score of 0.376. Oops, sorry. So it's basically just finding a probability like you did in Chapter 8 and 7. So we're trying to find the probability that we get a z-score greater than this, because you're kind of looking at what's the probability I would get this or more if we really think that our alternate here is that it's greater than 0.5. So our sign for what we figure out matches our null hypothesis. So we're looking at the probability Z is greater than 3.76. What happens when I do a greater than? Yeah, I got to do 1 minus the probability Z is less than 3.76. You guys don't have to get your formula sheet out, because we only need it for this one. Okay, here's the problem. Is 3.76 even on there? No, we go only to 3.4. So, see how it gets closer and closer to what? 1? So I'm just going to assume that it's 1. So we're going to do 1 minus 1, which would be 0. So this is my p-value. So it's taking something you already know how to do and just making new terms for it. Like the test statistic, you already learned how to do first semester. It's just a z-score. The p-value is just finding the probability. You guys have done all of this stuff before. You just haven't done it in this context. So like when we get tomorrow to our write-ups, the last part is usually the conclusion. So remember, p is low, reject the ho. So the first thing you got to do is kind of like write it out just in terms of do you reject or do you fail to reject. And then we write it out in like words. So our first sentence, since the p-value is 0, so since our p-value is 0, which is less than any significance level, pause. We didn't pick an alpha here because type 1 error, type 2 error, like, I don't think it would either matter. Like, people kiss one way, if they don't, it doesn't matter. So I'd pick like 0.05. But because it's 0, it doesn't matter which one we pick. Okay, sometimes they'll give you an alpha in the problem, sometimes they won't. Anyway, continuing our sentence. So since our p-value is 0, which is less than any significance level, there is evidence to reject the claim that the true proportion of couples who kiss to the right is 0.5. So your first sentence in your conclusion is always going to be take your number, compare it to your alpha or your significance level, and then tell me do you reject or fail to reject in context. You don't want to just say I reject the null hypothesis. Like you want to always give context. Now, since we're rejecting this, remember since we reject this, you're assuming this is true. So now we got to say that. And then it appears the true proportion is greater than 0.5. So again, the z value, the value of z, we call it the test statistic. And it tells us how many standard deviations the observed value is from the hypothesis value. So when you're doing a hypothesis test, it's customary to report the value of the test statistic with the p-value. So this is when we do a write-up tomorrow. The only thing we're missing basically from this section is the conditions. Okay, this is your, well, we had the testing for a confidence interval. That's kind of what this is. And your conclusions will look more like this. Okay. Tomorrow we'll put it all together, what we've done all week. Question.